In video 72 of Tensor Calculus, we'll continue our analysis of the surface covariant derivative. This time we'll extend the analysis to those tensors that do not lie in the tangent plane. In the last video, we limited our analysis to a vector t that was in the tangent plane. And because it was limited to the tangent plane, we could use this linear combination for our analysis. Well, if we're going to analyze a vector that lies outside the tangent plane, then this linear combination doesn't work. So instead of doing this, what we're going to do is to put in a linear combination using our ambient coordinates, ti and zi, like this. So by using our ambient coordinates, we can represent any vector that lies in the ambient space. So this is how we'll proceed. And of course we have to begin, as always, with the product rule. Okay, let's take a closer look at this term right here. We've got ti times the partial derivative of zi with respect to s beta. Well, first thing is that we can expand this second factor here using the chain rule. Because we can do that because our basis vectors zi are our ambient basis vectors, of course, but we're only working with those that lie on the surface of our surface manifold. So we can express zi as a function of s, and therefore, since that's the case, then we can use the chain rule to expand it. So we'd have ti times the partial of zk with respect to s beta times the partial of zi with respect to zk. All right, so again, so you understand that these two terms together are the same as this, expanding it by using the chain rule. Well, hopefully you recognize some of these things. The second factor here, this zk with respect to s beta, is nothing but our shift tensor that we ran into in video 60. So this is just zk beta. And then the partial of zi with respect to zk is something we ran into in video 28. It's the thing we analyzed to show that it can be represented as a linear combination of our Christoffel symbol, like this, and we'll had a linear combination with zm, like so. All right. So finally, let me reorder the terms a little bit. And I also want to do some renaming. I'm going to rename m to I and I to m. Okay, so we'll start with all the z k beta, but the k beta, and then we've got gamma. Instead of us renaming m to I and I to m, so this is what we'll have. And then we'll have T m right here and zi right there. Okay, so the whole point of this is that this term up here is exactly equal to this one. So we'll just use this as a substitution for this. All right, so all I've done is to replace this term with this one, giving us this. Okay, so the next thing we can do is, since we have zi in both terms here, we can factor that out and use what's left to define the surface covariant derivative as it relates to a contravariant vector component with an ambient index. And with that, we can rewrite this expression using the new operator. So we'd have the partial of our vector t with respect to s beta would be equal to this new operator times the covariant basis vector zi, which of course was not part of the definition. Okay, so what do we have? Well, in the last video, we derived two forms for our surface covariant derivative, one that applied to T alpha in the upper position and the other with T alpha in the lower position. So we had two forms, one for the contravariant component and the other for the covariant vector component. Well, here we have yet a third form of our surface covariant derivative, this time as it applies to a vector component with an ambient index in the upper position, a contravariant vector component with an ambient index. Okay, now notice that it is very similar to, but not identical to what we derived for the basic covariant derivative back in video 28. If we were to replace this with zk and remove this factor, then this expression would be exactly what we derived back in video 28. So in order to make this work, when we're doing a surface covariant derivative of an object with an ambient index, we need to include the shift tensor here. Okay, and notice too that when we use this new definition to expand this, we don't get an extra term out here. We don't need the extra term because the result is being expressed with the ambient basis, and the ambient basis is certainly capable of representing a vector that points in any direction. So we don't get any new term out here that points in the normal direction or anything like that. So in the last video, we found that this definition didn't change, but this result did. Well, in this case, the definition changes, but this doesn't. All right, so with that, and as you might expect, there's yet a fourth form for the vector component ti, where it's in the lower position for a covariant vector component. So let's repeat the exercise now and see what that looks like. This time we'll use this linear combination. We've got a covariant vector component and a contravariant basis. And as before, we'll start with the product rule. Now we'll take a look at this term right here and expand it out. We'll have ti times the partial derivative of zi with respect to s beta. And as before, we can expand this out using the chain rule. So we'll have ti and then the partial of zk with respect to s beta times the partial derivative of our basis vector zi with respect to zk. All right, so this first factor here is our shift tensor, zk beta. And for this term, we'll fall back on what we derived back in video number 32. And that is that this partial derivative is equal to negative gamma I km times our basis vector zm. All right, so now we'll rearrange some terms and do some index renaming here. So this is negative zk beta times gamma m ki tm times zi. So I'm sure you recognize that I've renamed m to I and I to m. So now all we have to do is to substitute this expression for what we have up here. So next we can factor out our basis vector, and what's left will give us the definition that we're looking for. And finally we can rewrite our partial derivative this way. The partial of our vector t with respect to s beta is equal to this new definition, which is our surface covariant derivative of our contravariant component with an ambient index, and we have to multiply by our basis vector here, which was not part of the definition. So what we have here is the fourth form that we were looking for. We've got the surface covariant derivative, this time of a covariant vector component with an ambient index. Now everything we said a few minutes ago is completely consistent with what we have here. Notice that if we changed this to zk and took out this shift tensor, this result is exactly what we derived back in video number 32. So it's almost like that definition, but with those minor changes. And also notice, of course, that we get this result down here. We do not have any extra term here. The basis vector here is sufficient to represent this vector in any direction. So the same message as before. There's a slightly different definition, but the result here is the same. Okay, so let's talk a little bit more about some of the properties of what we've derived here. Here I've summarized the two new forms for the surface covariant derivative that we developed a few minutes ago. Well, I said back then that the results are very similar to the normal covariant derivative, and as such, almost all the properties of the standard covariant derivative carry over to these forms. Well, I'll have more to say about that in the next video, but for now, let me just illustrate that by showing you what it would be like to apply this to a tensor of higher rank. So let's suppose we're going to find the surface covariant derivative of a second rank tensor of indexes I and j, like this. Okay, well, we go through the same kind of pattern that we developed back in videos 34 and 35. The concept is exactly the same as then, and you could go back to videos 34 and 35, follow through with the same development we did there to show that the pattern is the same. So it begins, as always, with a partial derivative of our tensor, Tij, with respect to S beta. And then because we have two indexes, we're going to have two additional terms out here. Now the first in the upper position dictates that we need a positive term, but this time it's this pattern up here. I need to include the shift tensor, zk beta, times our Christoffel symbol, and this is our dummy index always. Okay, with an upper index then, I want to form a contraction using the upper index. So when I put the tensor here, this is my dummy index here and here. Then we have I there and j here. Okay, now for the lower index, I'm going to need a negative term. Again, I start with my shift tensor and the Christoffel symbol. K is always here. This time the dummy index is going to be in the lower position, so it's here and here. I is here, and j is there. And so that's it. It's the same pattern that we developed back in video 35. All right, with that having been done, I now want to show you a property that exists exclusively for the surface covariant derivative as it relates to tensors with ambient indexes. Okay, to develop that, we'll start this way. Our vector component ti, of course, can be expressed as a function of s. In fact, that's the reason that we're able to take the partial derivative with respect to s in the first place. But of course, that can also be expressed as a function of z, which is a function of s. And this relationship is true because we're only interested in evaluating these vectors for points on the surface itself. So this relationship holds true for all values of z that lie on the surface of our manifold. Okay, now with this being the case, we can now take the partial derivative of ti with respect to s beta, and on the right side, of course, is the chain rule. So the partial derivative of ti with respect to zk, for example, times the partial of zk with respect to s beta. So that just completes the chain rule. All right, well, this second factor is nothing but our shift tensor, so I'll replace that with zk beta and follow through with this other term right here. Partial of ti with respect to zk. All right, now that means that this term, which is the same as these terms up here, can be replaced by this. And when we do, you'll notice that this factor is common to the other terms as well. That means as we do this, we can factor the shift tensor out of the expression, leaving the other terms added together. So let's do that. Okay, now notice that if I distribute this factor back to here, then the product of these two terms right here is the equivalent of this as per what we did down here. And of course, distributing it to this term just gives us this again. So these two are exact equivalents of each other. So let's do the same thing now for the second expression. Now what you'll notice is that this is the expression for the normal covariant derivative with respect to k, as is this. These are the two different forms that we developed back in videos 28 and 32 respectively. So we can replace this with the normal covariant derivative. Now what we've developed here is known as the chain rule. It shows us that the surface covariant derivative of Ti is related to the normal covariant derivative of Ti by simply adding our shift tensor. And the same is true right here. Okay, so this is a very interesting and also a very useful property of the surface covariant derivative as it relates to objects that have ambient indexes like Ti. All right, now, for example, we know that this normal covariant derivative over here is such that objects like Zi and Zij and delta Ij and so on are objects that possess the metronyllic property. So if we apply this expression to any of these, we're going to get 0. Well, because we have this expression, that tells us that applying this operation to these objects will also produce 0. In other words, the metronyllic property for all of these objects is true not only for the normal covariant derivative, but for the surface covariant derivative as well. You remember we lost the metronyllic property for the surface basis vector, but that's not the case for our ambient basis vector. None of the metronyllic properties are lost in the process. Okay, now this chain rule applies equally well to tensors of higher rank. So let's demonstrate it in this last example here. The same way we worked this out before, you can see that the partial derivative of Tij, which can be expressed as a function of s, is also a function of z, which is a function of s, which means we can apply the chain rule, and when we do, we're going to get this expression, zk beta times the partial derivative of Tij with respect to zk, and as before, this expression right here, which is this one, can be replaced by this. A factor of zk beta comes out, and the result is that we have the factor of zk beta, and what's left when we factor that out is nothing but the normal covariant derivative of a higher rank tensor Tij. So again, we see that the surface covariant derivative here is equal to the normal covariant derivative times our shift tensor. And in fact, the same thing works for any case where the tensor is expressed exclusively with ambient indexes. It does not work if they're mixed. If we have some surface indexes in here, we can't do this. But if all the indexes are ambient indexes, then the chain rule is applicable. Okay, I think that's enough for today, so let's end the video with a brief recap of what we've done. The first thing we did was to derive these two new forms relative to vectors that are non-tangent vectors, vectors that do not necessarily lie in the tangent plane. And to do that, we had to express our vectors using ambient indexes. We can't use surface indexes because that only limits us to vectors that lie on the tangent plane. Okay, now we pointed out that these two new forms are very similar to what we derived for the standard covariant derivative back in videos 28 and 32. You'll notice if we replace these with zk and we take out the shift tensor from both expressions, we have exactly what we derived in videos 28 and 32. Now, even though these definitions are slightly different than anything we've seen before, we can use them in a form that's very familiar to represent our partial derivative of our vectors. So the partial derivatives of our vectors with respect to s beta is expressed simply as the linear combination of each of these two forms up here. So that's very simple and very familiar. We do not see an additional term out here like we did in the last video. Okay, and we said that because these definitions are very similar to what we derived for the standard covariant derivative, that virtually all of the properties carry over, and we use that to illustrate what it looks like to take the surface covariant derivative of a higher rank tensor. It turns out to be this form. And again, that's very similar to what we derived back in videos 34 and 35. So again, if we replace this with zk and took out our shift tensors, this is the exact form we'd have if we took the standard covariant derivative of a second rank tensor tij. Okay, and finally, we derived a property known as the chain rule. And the chain rule says that our surface covariant derivative here is equal to the standard or normal covariant derivative multiplied by our shift tensor. And this turns out to be true in any case where the tensor is expressed exclusively using the ambient indexes. Does not work if we have any surface indexes in here, but as long as all the indexes are ambient indexes, then this chain rule applies. Okay, in the next video, we're going to do a more comprehensive analysis of the overall properties of the surface covariant derivative, including the forms that we've derived here, as well as the two forms we derived in the previous video.